One of the most important classes of relations are functions. And functions are something that ordinarily people bump into first in math classes, but in computing functions are very important. And let's go into some detail about that. Anyway, um, a function is a relation, so one way to think of it, this is not necessarily the way that people think of it most productively, is that you have a relation on a set A cross B. So I'll call the relation R. And so the relation um, involves ordered pairs, something from A and something from B. A and B can be any kinds of sets. And so that's just a relation. And it's interesting, one of the ways that we've represented relations, which is more of a conceptual way than an actual, strictly speaking, logical way, is to have some kind of picture of A cross B, and then the relation might be this subset that I've done in a different green. So now, A and B may not have an imposed order that everyone agrees on, so this picture can be a little bit deceptive. If you have something like the real numbers or the integers, where 2, 3, 4, 5, and so forth and so on, then that is actually a graph, and that would be the graph of some relation. So that's relations in general. A function is a relation with a special property, and the property is this: to be a function, the colloquial way to say it is that in all the ordered pairs that make up this relation, each entry of A occurs no more than once. It may not occur at all, but it never occurs more than once. And that's a little bit of a mouthful to put into symbols, but I'm going to do it. So this relation R is a function if we have A B1 in R and A B2 in R. So I've got a couple of potential ordered pairs that are inside this relation, and they have the same first entry, the same entry from the set A. And so the distinction here to be a function is that if this happens, then B1 and B2 actually must in fact be the same. So that has to imply. Now this is reasoning implication, not truth table implication, but that somehow has to imply that B1 is B2. So that is the basic definition of function, and it's perfect. It's almost too perfect. It's really hard to use that definition to come to understand things about functions, or as part of your vocabulary about talking about functions. But that is the definition. So we have to work with that and see what goes on. So let me give some examples of functions, and there's a math example, and this one's interesting. We'll come back to this one later as well. Let's look at f of x is 1 minus x squared. So this is the kind of function that you might have come into in a math class, and so x is the variable. Usually from context or explicitly, you know what set x is from, and it's usually the real numbers, and the pair that, or the other half of the pair corresponding to x, is 1 minus x squared. So this function that we've used the standard function notation for. Really, if you wanted to write it as a set, this is the set of all pairs x comma 1 minus x squared, and I'll just make the x, say, be a real number. So there's the function as an ordered pair, and you can see that you've got x and 1 minus x squared. And the thing is, because of the way we compute this, then you know when x is 3, 1 minus x squared has to be 1 minus 3 squared, and when x is a half, 1 minus x squared has to be minus a half squared, and those are well-defined operations, and so there's no ambiguity in what happens for a particular x. And so that's what this says here. For a particular x, oh, you don't have any ambiguity. You get the same thing. And that's what happens with these functions from as they're used in math. And so there's the situation. Now, in general, because this brought up the question of, what set is A, what set is B, and having said that, this leads to a very common notation, In fact, it's so common that some people seem to believe that it's the only notation, which it is not. But the very common notation is this. In the previous example, the function was called f, and so I'm going to use f. And instead of writing that f is a subset of r cross r with certain properties, so that's the way it would seem to be following the original example. But instead of writing it that way, I'm going to say, no, we don't write it that way. I'm going to put a line through it. We say f goes from r to r. So that's the way that we write these. If we want to go back and say, back up here what's gone on, we would say here that r goes from A to B. So there's the notation, very important. And so more important on the math side than on the computing side. And we're going to do some computing functions, and you'll see that people don't talk this way about computing functions, but we'll continue. Okay. Now, in fact, there's some vocabulary that is very useful and very commonly used, and so let's introduce it. So if I have a function f from A to B, and A to B might be any kind of set, and so we're seeing the property here. Now, it doesn't necessarily have to be a numerical function. It could be another kind of function. We've got some names for these things. A is called the domain, and B is called the codomain. Now, you might have heard a different word, which you're going to hear again in a few seconds, but that's actually what's going on here. So we're saying the first part of the ordered pair that this function contains comes from A, or comes from the domain, and the second one comes from B, comes from the codomain. The word that you might have heard, which is very, very common, is to talk about the range of f, and that is best described using set language as the following. It's the set of B such that there exists an A. A is from the set big A, with B equal f of A. I think I got the right number of parentheses there. So that's the range. So the domain is where you come from, or the first part of the ordered pair. The codomain is the set you end up in. You may not hit everything. I'll show you an example of that as well in a second. And so that's the codomain. And the things that you actually hit are the range. So when you go to the target range, actually hit your target. It's almost the same thing. Okay. So just to look at some examples, if we have, I'll just use some math functions to start with. If you have f of x is given by the reciprocal of x, the domain is, I'm just going to write this informally, is the set of x that isn't equal to 0. So that's this function. There's its formula. The formula is what the function does to x. So that's the domain. And the codomain is the reals. And the range is the reals. Well, you may not get 0. It depends on your mood. So I'm going to say the range is r minus 0. For another example, I'm going to change letters so we don't mix them up. I'm going to say q of x is x squared. So that's just the squaring function. multiply the input by itself. So the domain is R, and the codomain is R. I'm using this Blackboard bold R to represent the real numbers. And the range, well, the thing is, when you square things, you can't get a negative number by squaring. So the range is the set of y with the property that y is greater than or equal to 0. And if I do a quick cartoon of the graph here, you'll see that. So I'm kind of highlighting the range. So from the get-go, the output of this function is a real number, so that makes the codomain the real numbers. And then when you start to examine it more closely, you realize, oh, no, I don't get all the real numbers, and that what you actually get is the range. Okay, so I think that's enough to get us started here. And so there are a couple of other properties of functions that, or I'm sorry, a couple of other ways of looking at relations that we should see what the function condition says about them. And so let's look at this relation that we've looked at before. And so this is as the directed graph or digraph of a relation. And we've been talking about this function on a set with 6 elements. I'm sorry, it's a relation. It's a relation. It is not, in fact, a function. And so what's gone on here is we've got 6 elements, and remember the relation is above in the diagram. So the direction I'll put in the arrows, and so there we are. Now this is not a function, and the reason that it's not a function is if we look at this node that I've circled here, what happens is you've got an ordered pair of that node and the one on the left, that node and the one on the left, and you've also got ordered pairs with that node and the one on the right. Well, that means there's ambiguity. When you get to that node, you might go this way, you might go this way, and so this is not a function because of that one node. And so the graph characterization of functions is no node has more than one edge, directed edge, coming out of it. So, so the condition is to be a function no more than one out edge per node. So remember, when in the digraph representation, you've got, starting down here with my thumb, you've got a node here and a node here, and if there's an edge between them, that means the thumb, comma, index finger, or whatever they're pointing to, is an element of that relation way back using the original definition of relation. Okay, so so that tells you about the digraph picture of relations. And let's now talk about some functions that come up in computing. Now, functions have a lot of properties, and so I'm going to have to split this up in 2 videos to cover all of the properties, but we want to make sure we have the basic idea of what it is that we're talking about. So in computing, we have lots of functions that aren't necessarily numerical. I mean, if you go by Turing machines, eventually everything's numerical, but in practice, they are not numerical. And so I want to mention some functions that are used in computing. And here's an easy one. Now, in computing, a lot of times, like if you take the C or the languages that were developed from C and take the declaration of what a function is. So in C, you might, this would apply to other languages as well, but I'm old and I use C. So you have something like int square int x. So my int seems to look like an F. That's confusing, sorry. So this is how you declare a function in C. This says that the input, the domain is int. Now that's a type, but it's kind of like the integers, but it's a finite set. And the codomain is int. And so that's again is like the integers, but it's a finite set. And so in most declarative programming languages, when you define a function, you specify the domain and codomain, usually as bigger the types that are defined within the language. And now you can use object overloading and come up with more exotic types, but whatever the function is, you have to say what the output is. There is a funny kind of function in C and other languages that were developed from C, which the output is called void, V-O-I-D, and that says there is no output. So sometimes in computing there is no output. There's something that happens as an effect of doing the computation. But that is discouraged in programming. So you could say void, and I would avoid void, and if you can. Okay, so I'll fix this later when I take a picture of the notes to make that more look like int. So here's a function. I'm going to call it car strip, and I'm going to make up a type called string. And so that I'm saying here that the input is a string. You might have to vary that from language to language. And the output is actually, I'm going to change that to string. So this is a string manipulation function. And so the input is a string, the output is a string, and I'm going to specify the function by what it does. I'm going to just say, write it out in words, remove all the vowels. Now, as long as we all agree on what the vowels are, that's A, E, I, O, U, not sometimes Y. We're going to say Y is a consonant for this purpose. So you give me a string. If I take the string like remove all vowels, this is a very CS thing to do, is the string example that you use to illustrate your string function is the string about the function. So if I have the input is the string remove all vowels, no spaces. I guess you could have spaces, but so what does this function do to this string remove all vowels? Well, having a CS sense of humor, we just remove all the vowels. So I'm just going to strike them out. E, O, E, A, O, E. So what's left without being struck by the red pen is the output of this function. So input, remove all vowels. Output is R, M, V, double L, V, W, L, S. It's a thing you might do. Another example of a string function or of a more broadly computational function is sorting. So I'm not going to specify the preamble there because we can sort so many things. We can sort integers, we can sort cars, we can C-H-A-R-S, cars. Well, we could sort cars. You could take a lot full of cars and sort them by serial number. I'm not sure actually I can think of a lot of good reasons to do that, and if you want to process something about them. So anyway, so sorting is a function, and the input is a string and the output is a string, and they happen to have the same length, but the output, if you put in a string and sort it, the output will be in alphabetical order. And so I'll just kind of leave it with that sorting is a function. Now, there's an interesting thing that happens with functions in general, and let me mention this, and like I said, we're going to have another presentation about functions because, well, there's just an awful lot of vocabulary to cover. Remember we talked about composing relations, and I shouldn't talk and write at the same time. Composition. So composing relations is something that we've talked about, and so we can compose functions. We can do that as a mathematician or computer scientist would say. We can do that trivially because we can do it to relations. So we're talking about the same thing that we do with relations, but it's often more interesting to see what the composition is that goes into a function. So I'm going to take the function, the math function I talked about at the beginning, and so that was given by the formula 1 minus x squared. And I'm just going to break that down as a composition of functions, and this introduces a very common notation for working with functions. So what has happened here is I've done the function that sends x to x squared. Oh, excuse me. So the notation is this arrow with kind of a little fence on the end. So the arrow without the fence, that one's up here, that says, that goes between sets. This arrow with the fence says what happens to a particular element. So what we've done here is I said, oh, here's a function, and the function is what it does. It sends its input to the square of its input, and then we're not done yet. To get the whole function, we have to go to 1 minus x squared. So we can annotate those arrows with words or symbols or something. So this is the first function there is the squaring function. That's x goes to x squared. And the next one is the subtract from 1 function. That is a function. It's very simple. So the function that I started with here is actually a composition of two simpler functions. So on the computational side, you could take this remove all vowels function and take the output from that and sort that output. That would be a composition of functions. You start with a string and then remove all the vowels and then sort the output, and that is a composition of functions as well. And in operating systems like Unix or Linux, those are built into the operating system by the concept of pipe, P-I-P-E. And so this pipe concept that goes into Unix or Linux is in fact the composition of the functions. Anyway, this is a good start for all of the vocabulary about functions, and there will soon be a second presentation about some of the properties that functions have.